This informational video is designed to increase awareness about the risks of accidentally mixing sodium hypochlorite with other incompatible materials. It represents a compilation of current experience and knowledge drawn from Chlorine Institute members. The video is intended for general awareness only and is not intended as a substitute or replacement for on-the-job training or written standard operating procedures, guidelines, or checklists. Sodium hypochlorite is commonly referred to as bleach. You may think there are some similarities between chlorine and bleach, and in fact you may have heard bleach being referred to as chlorine bleach or liquid chlorine. But it is critical that you understand that while chlorine is used as a raw material to produce bleach, bleach is not chlorine. First, they are placarded differently. The U.S. DOT classifies chlorine as a Division 2.3 poison inhalation hazard gas and bleach as a Class 8 corrosive, which have very different characteristics and hazards. One of the first things you need to assess upon arriving at an incident is the chemical involved, which will dictate what type of response plan you need to activate. Chlorine is shipped as a compressed, liquefied gas. The only time it arrives at a customer's facility in gaseous form is when it is a direct pipeline from the producing facility. Household bleach is always an aqueous solution. While the accidental mixing of sodium hypochlorite during delivery may not be a frequent event, it can result in serious consequences, such as severe injury. Sodium hypochlorite is highly reactive. When sodium hypochlorite is mixed with acids or acidic compounds, nitrogen-containing compounds such as ammonia, or organics or fuels, it creates a violent reaction that releases chlorine gas and, in some cases, explosive compounds and/or chlorinated organics. These can all result in serious injuries, including chemical burns and toxic gas inhalation. Unintended consequences can occur through accidental mixing. The mixing of sodium hypochlorite with an acid is very dangerous due to possible chlorine gas generation. Chlorine gas is a toxic inhalation hazard, TIH. The odor threshold for chlorine is 0.2 to 0.4 parts per million. Inhalation exposure to a concentration as low as 1 part per million may cause irritation of the nose, throat, and respiratory tract. Moderate irritation of the respiratory tract will occur at 5 to 15 parts per million. At 30 parts per million, there will be immediate chest pain, vomiting, shortness of breath, and cough. Toxic pneumonitis and pulmonary edema can occur following exposure to 40 to 60 parts per million. At 430 parts per million, chlorine gas exposure can be lethal after 30 minutes. Exposure to chlorine gas at 1,000 parts per million is fatal within a few minutes. Sodium hypochlorite is also not compatible with the following materials of construction: metals such as copper, nickel, iron, or cobalt. Copper, nickel, and cobalt and their alloys act as a catalyst for the decomposition of sodium hypochlorite. Nonviolent release of oxygen gas could cause overpressurization of closed vessels or systems. In this video, you can see on a small laboratory scale what happens when an acid is introduced to a quantity of bleach inside a fume hood. There is a violent reaction that generates heat and the evolution of greenish-yellow chlorine gas, which you can see accumulating in the flask since it is heavier than air. Because this was done in the hood and there is more chlorine produced than the flask can hold, you can also see some escaping out of the flask opening and being pulled up and away because of the fume hood's draw. The Chlorine Institute routinely analyzes incident data to find opportunities to improve and enhance safety in the chlor-alkali industry. Accidental mixing incidents are of particular focus and interest to the Chlorine Institute because of the serious consequences that have occurred from these incidents. Let's examine contributing factors in 2 case studies involving accidental mixing incidents.
October 21st, 2016. The MGPI processing facility in Atchison, Kansas. An unintended chemical reaction resulted in a dense cloud containing toxic chlorine gas and other chemicals that drifted into the community, leaving over 140 people with reported injuries. The incident occurred during a routine chemical delivery when two incompatible chemicals, sulfuric acid and sodium hypochlorite, were inadvertently mixed, forming the toxic cloud.
Delivery and unloading operations may be perceived as simple compared to other processes at chemical facilities. But because these activities can involve large quantities of chemicals, the consequences of an incident can be severe. Our case study on the MGPI incident stresses that facilities must pay careful attention to the design and operation of chemical transfer equipment to prevent similar incidents.
The MGPI facility produces distilled spirits, specialty wheat proteins, and starches. The incident occurred in a section of the plant that uses sodium hypochlorite, or bleach, as well as sulfuric acid. These two chemicals, when combined, can form chlorine gas and other chemical compounds. On the morning of the incident, a truck from a chemical distribution company, Harcross Chemicals, arrived at MGPI to complete a routine delivery of sulfuric acid. After reviewing paperwork in the control room, an MGPI facility operator escorted the driver to a locked loading area. There, chemicals are transferred from trucks into the facility through piping, called fill lines, to several large storage tanks in an outdoor tank farm. The MGPI operator unlocked the sulfuric acid fill line for the driver to connect the truck's unloading hose. The operator remembers pointing out the correct fill line to the driver before he returned to his workstation. The driver, however, does not recall hearing the operator identify the fill line. Unknown to the operator, the sodium hypochlorite fill line was also unlocked, and the two lines, which were only 18 inches apart, looked similar and were not clearly marked. The driver connected his truck's sulfuric acid hose to the sodium hypochlorite line, and sulfuric acid began flowing inside. He then returned to the cab of his truck. Shortly before 8 a.m., a greenish-yellow gas began flowing from the bulk tank of sodium hypochlorite. The driver noticed the cloud in his truck's side view mirror and attempted to return to the connection area to turn off the flow of sulfuric acid, but the gas overwhelmed him. He then ran to the passenger side of the truck to close a valve that could halt the flow, but he was prevented from doing so by the gas. Instead, he ran away from the cloud and escaped to a separate area of the facility. At about the same time, toxic gases entered the facility control room through the building's ventilation system. MGPI operators preparing for shift change in the control room were immediately overcome by the toxic gas. Because the operators had a practice of locking respirators between shifts, some were unable to access their respirators before evacuating the building. With no other way to stop the flow other than closing manual valves on the fill line or truck, or by triggering one of the truck's emergency shutoffs, the sulfuric acid continued to enter the sodium hypochlorite tank for nearly 45 minutes until emergency responders shut down the flow. Approximately 4,000 gallons of sulfuric acid combined with 5,800 gallons of sodium hypochlorite, causing a large, dense cloud containing chlorine gas, which soon drifted off-site. MGPI employees were evacuated from the site, and 11,000 Atchison citizens were advised to either shelter in place or evacuate. Over 140 people, including MGPI employees, emergency responders, the truck driver, and members of the public, sought medical attention, some requiring hospitalization.
The CSB's final report includes 11 key lessons and outlines clear safety improvements that can be implemented at similar facilities across the country. Among these are facilities should evaluate chemical unloading equipment and processes and implement safeguards to reduce the likelihood of an incident, while taking into account human factors issues that could impact how facility operators and drivers interact with equipment. As the CSB report details, the contributing factors included close proximity of fill lines for incompatible materials, indistinguishable fill lines for incompatible materials, insufficient pipe marking and labeling, insufficient and inconsistent unloading procedures, including no practice of identifying procedure deviations and ensuring compliance with procedure, insufficient training, lack of an automatic emergency shutoff for the unloading process, poor ventilation system design, improper storage of and access to escape respirators, and insufficient communication between various parties, driver to operator, at plant shift change, to emergency responders and the hospital, and to the public. The CSB findings reaffirmed the need for facilities to pay careful attention to the design and operation of chemical transfer equipment to prevent similar events. We will now move on to the second case study. On April 2, 2014, a driver was scheduled to deliver ammonium sulfate to an unstaffed water treatment facility in Kitchener, Ontario. Ammonium sulfate was accidentally delivered into a sodium hypochlorite tank. The reaction was so violent, there was damage to the roof of a multi-story building. There were concerns that nitrogen trichloride, a reactive byproduct, was still present days after the explosion occurred. The incident received multi-day news coverage, and 12 days after the incident, there was initial speculation that the building would need to be demolished due to structural issues, but those were unfounded. Later, an estimated $800,000 would go to the water treatment plant for repairs. An investigation determined that the cause of the explosion was human error. A contractor accidentally pumped a chemical into the wrong tank, causing a reaction. The corrective actions that were taken included installing locked cabinets with correct signage and closing the delivery connections. Accidental mixing incidents often have similar contributing factors, including the two case studies we just reviewed. In summary, the following are common contributing factors in accidental mixing incidents. Storage tanks or connection points may not be labeled or marked correctly or at all. Connections for the different product storage tanks look the same. Insufficient or lack of documentation for the process of receiving and unloading of materials. And a lack of awareness by unloading personnel of the potential catastrophic consequences of accidental mixing incidents. Additional factors that also contribute to accidental mixing include poor communication by unloading personnel due to complacency, interruptions, or rushing to another task. Shipping papers or tank labels may not be reviewed thoroughly. The driver does not question or raise concerns with the plant operator, and inadequate training of delivery and receiving personnel. Next, we will watch a dramatic reenactment of an accidental mixing incident resulting in a tragic outcome.
Bye-bye, see you at tea time.
Bye-bye, don't forget to be safe.
I won't, give me a kiss. Bye, love. Hi, Chris. I've got your delivery of sodium hypochlorite.
Look, I'm in a hurry. I've got kids coming in the next 5 minutes. You know where the connection is, don't you?
Yeah.
I'll be back in 5 minutes.
Wait up. There's no label on that connector. You sure that's the hypo, yeah?
Yeah, of course it is. Look, I've got to go.
I'll just proceed then. All right.
Get on with it. I'll sign your paperwork later, yeah?
Keep him under close observation, ventilate, transfer him to intensive care.
What happened to him?
I believe he was delivering sodium hypochlorite to a swimming pool. Connected to the wrong outlet, creating serious chlorine gassing and mass panic. The next 24 hours are crucial. You should make it, but you never know. He may recover physically, but I'm not sure how he's going to feel psychologically when he realises that his actions have caused fatalities. That's something he's going to have to live with for the rest of his life. You've thought his company would have had strict procedures to follow.
Bye-bye, don't forget to be safe.
Preventing accidental mixing incidents requires suppliers, customers, and drivers to take active precautions. Written procedures should be developed that employ verbal and visual confirmation between the delivery and receiver personnel. Employee training should be conducted. Active monitoring for compliance with the written procedure is essential. Let's review some suggested safeguards that can be taken. Extreme care should be taken to ensure cargo tank contents are properly identified. Verify the cargo tank contents by careful inspection of the bill of lading. Ensure that the chemical name, UN number, trailer number, and all placards match the bill of lading. If any doubt, notify the shipper for verification before continuing. Visually trace the pipe run from the connection point to the receiving tank to ensure the product is directed to the correct tank by matching the lading information with the tank labeling. If unable to confirm, or the piping goes to an unmarked storage tank, do not begin the transfer process and make appropriate communications to the customer and dispatch. During the transfer, the driver should maintain an unobstructed view of the unloading operation. Customers should locate sodium hypochlorite unloading connections away from incompatible product loading and unloading connections. Design piping to the minimum length that is needed to achieve a safe loading-unloading process. Piping should not be excessively long, which could unintentionally introduce other issues. Piping should be marked clearly so that the unloader can trace the product piping from the connection point to the receiving tank. Sodium hypochlorite unloading lines should be dedicated to avoid any compatibility issues. A lockout system should be considered to prevent accidental mixing. For customers designing new systems, consult with your supplier for design considerations. An inspection checklist that contains all the steps should be used by the customer for transfer operations. The checklist should be utilized to verify each step as it is completed. At a minimum, the following should be completed prior to the initiation of the transfer. Verifying the correct chemical by matching the UN number and chemical description on the bill of lading with the tank's contents. Ensuring that the certificate of analysis information matches the trailer number if provided on the certificate of analysis and the product name. Verifying other information on the bill of lading, such as the trailer number and security seal numbers. Confirming that the transfer hose is connected to the correct unloading line. Verifying that any common drain sump used for multiple products is empty, rinsed, and isolated prior to beginning the unloading process. And ensuring that the tank has sufficient capacity to hold the amount being delivered. Suppliers can put in place the following safeguards by utilizing a loading and unloading checklist, which should include verifying that trailers have the proper last contained or washout certificates, visually verifying that trailers are clean and empty or have only residual sodium hypochlorite prior to refilling, applying numbered seals and noting seal numbers on the bill of lading, and verifying that the proper placards are in place on the trailer and that they match the bill of lading. Other safeguards that suppliers should put in place include offering to train carriers and customers in safe handling practices, including the avoidance of mixing chemicals, utilizing a bulk delivery pre-qualification process that reviews the customer's site prior to the first delivery, periodically updating the bulk delivery qualification information through inspections of customers' facilities, encouraging drivers to raise safety concerns and ask questions, following up appropriately to driver concerns and questions. If a customer is not observing the delivery, additional precautions should be in place. Incorporating safety policies regarding bulk deliveries that empower drivers by providing strong management support and giving drivers stop work authority. It is important for suppliers to work with facilities and collaborate to develop or agree upon procedures for chemical unloading. The Chlorine Institute has many resources available to download related to accidental mixing. Please visit the CI website at www.chlorineinstitute.org to download Pamphlet 96, which includes useful information such as the resources listed here. Additional resources related to accidental mixing that can be found on the CI website include Sodium Hypochlorite Incompatibility Chart, available online in Spanish, the Hypo DVD, Handling Sodium Hypochlorite Safely, an accidental mixing poster, and a sodium hypochlorite customer's generic safety checklist, bulk users. The information contained in this video is drawn from sources believed to be reliable. The Institute and its members, jointly and severally, make no guarantee and assume no liability in connection with any of this information. Moreover, it should not be assumed that every acceptable procedure is included, or that special circumstances may not warrant modified or additional procedures. The user should be aware that changing technology or regulations might require a change in the recommendations herein. Appropriate steps should be taken to ensure that the information is current when used. These suggestions should not be confused with federal, state, provincial, municipal, or insurance requirements, or with national fire, building, or safety codes. The Chlorine Institute exists to support the chlor-alkali industry in advancing safe, secure, environmentally compatible, and sustainable production, distribution, and use of its mission chemicals. CI's mission chemicals include chlorine, sodium and potassium hydroxides, sodium hypochlorite, the distribution of vinyl chloride monomer, VCM, and the distribution and use of hydrogen chloride. This support extends to giving continued attention to the security of chlorine handling operations. Chlorine Institute members are committed to adopting CI's safety and stewardship initiatives, including pamphlets, checklists, and incident sharing that will assist members in achieving measurable improvement.